morning, friends. We have been discussing very preliminary things about stability augmentation system. Although they are preliminary, but they are very fundamental in nature. When we will be doing some higher level course, we will understand how important are these understanding. And we have kept our focus on the damping ratio and natural frequencies. And we have been telling that we are concerned about the handling qualities of the airplane, because the pilot has to be comfortable, passenger has to be comfortable. And there are, based on experience, based on empirical data, based on a lot of psychoanalysis, there are some guidelines that has been postulated which somehow give guidelines for handling qualities. So I will just glance through those. And these handling qualities are postulated in terms of, we'll see the damping ratio and natural frequency of particular mode. For example, there's the phugoid mode. So these handling qualities will tell what should be the limit on damping ratio. If it is short period, what is the limit on natural frequency or damping ratio, based on type of aircraft, based on type of flight phase, okay, and based on the failures. For example, if you are designing a large transport airplane, the criteria will be different than a light weight airplane. For a large airplane, the additional criteria will be, even if one engine fails for a multi-engine aircraft, the aircraft should have minimum these performance characteristics. It should be able to execute those, that with a single engine it should be able to have a climb of this much, its natural frequency or its damping ratio should be this much, or it should be able to complete the flight phase, or it should be immediately abruptly cut down the flight phase. All those things will come, and to understand that, to make it more systematic, the airworthiness committees in association with designers, they have given some criteria, some guidelines. In that first, what they have done, they have defined airplane classes. So in class 1, Class 1 includes or addresses light utility aircraft, primary trainer, and light observation aircraft. Okay, so that all those aircraft which comes under light utility aircraft category, they are classified as class 1 type aircraft. In class 2 type, you have heavy utility, like maybe search and rescue. It also has light, medium transport, cargo tankers, then early warning system, anti-submarine, and there's so many other type of aircraft which are summarized in class 2. And in class 3, there are large, heavy, low to medium maneuverable aircraft, like heavy transport, cargo airplane, then trainer for class 3. All this type of airplane are classified in class 3, and class 4 is high maneuverability aircraft, just like fighter, interceptor, the trainer of class 4. You'll find many such type of airplane. If I add one more, it is tactical reconnaissance. Like that, okay. So what is the first approach? Depending upon the type of aircraft vis-a-vis type of performance required, there are 1, 2, 3, 4 category or classes of aircraft, okay. This is one. Second comes is definition of flight phase. So what was the first? How it was characterized to give you a complete idea about handling qualities. first thing was you identify this aircraft belongs to which class, class 1, class 2, class 3 or class 4. First exercise is this. And which aircraft should be class 1? You have to check. Is it light utility? Is it primary trainer? Is it light observation? Like that, you have to make a judgment and you classify the airplane. So after the class or classification based on the type of aircraft, we are now discussing about definition of flight phase, because all these handling qualities, it is not only important whether it's a light utility aircraft or whether it's a high maneuverability aircraft, we need to know about the flight phase and how they are characterized. That I am now going to list out. Category A, and that is like air to air combat. Then B, I am listing few of them. Ground attack. I have started with military aircraft, so forgive me. I do not believe in war and all. At the same time, we should be strong enough so that nobody can dare to trouble us. So it's important we know all these things. In-flight refueling. You have then close formation flight. There are many you can Google through and you will get. This material I am presenting, referring book by Roscom. Okay. So this is category A, which is defining the flight phase. We also have category B, and in that we will have climb. The flight phase is climb, cruise, loiter, descent, emergency, deceleration, and aerial delivery. I am just mentioning few of them, right? So this is category B. That means we are now defining different flight phases. In category A, these are the flight phases that is included. In category B, climb, cruise, loiter, descent, emergency deceleration, aerial delivery. These are the flight phases categorized under category B. Similarly, you have category C. In category C, you have takeoff, you have catapult takeoff, you have approach, you have landing, and many more, right? That comes for category C. So what we have seen, how it has been handled, how the guidelines have been structured. First, we look for the airplane classes, which class the airplane belongs to, looking at these attributes. If it is in class 1 or class 2, then we check the flight phases, whether it belongs to category A, that is it the air-to-air combat airplane, or is it the air-to-air combat flight phase we are talking about. Similarly, if I want to go for category B, I need to look for cruise, climb, loiter, all these flight phases. And category C, the takeoff, catapult, takeoff, approach, landing, etc. These are the flight phases under each category. So we have classes, we have categories. Now we are talking about level. When you say level 1, it means flying qualities, clearly adequate clearly adequate for mission flight phase. For mission flight phase, let me write the second one, then I'll explain. For level 2, flying qualities adequate, however, but pilot has to put extra effort. Okay, and this level 3, you could guess now what is level 3. Flying qualities such that the airplane can be controlled safely. Flying qualities adequate to control the airplane or aircraft safely however excessive workload on the pilot. I'm not writing everything, just to give the quality statements which are good enough to excite you and read through different textbooks. The level 1 says flying quality is clearly adequate for mission flight phase. It's absolutely fine. So level 1 aircraft. Level 2, it is adequate, but little bit of pilot has to put extra effort, right? And level 3 is flying quality is adequate to control the airplane, right? That means the pilot has to now put lot of extra effort. So that is the level 3. That you should understand. These 3 levels, level 1, level 2, level 3, are extremely important. So what is the approach now? You could see first we identify the class of aircraft, then we identify the flight mission or flight phase, and then we are saying now there are level 1, level 2, level 3 handling qualities. If the handling quality is such that it's clearly adequate, pilot nothing extra he has to put, level 1 aircraft. Level 2, little bit you have to put, and level 3 is quality is good enough for safety, to control the airplane from safety point of view, but lot of excessive effort comes from the pilot. That is the level 3 handling qualities, right? Now, with these 3 understanding, now we will come back to how these things are quantified through zeta, omega n, etc. So I will only give some representative number. Once we identify class, category, and level, handling qualities level, as I told you, we will be looking through the damping ratio and natural frequency or different modes. If I take Phugoid mode, the requirement is for level 1 qualities. For level 1, you have to ensure that zeta Phugoid is greater than or equal to 0.04. For level 2, it should be zeta p greater than or equal to 0, and level 3, time to double for Phugoid is greater than 55 seconds. Do you understand? Time to double for Phugoid, you know Phugoid is this. Time to double means it is actually going on increasing, right? So whenever it is diverging, we say time to double, and whenever it is converging, we try to use time to half. That is time to double the amplitude. This is time to half the amplitude. Okay. So let us see something on time to double in phugoid, and you know that the phugoid response I can write in terms of A e to the power minus zeta phugoid omega phugoid t into sine omega phugoid plus phi. Right? The phugoid response I can express like this. It is like sinusoidal with a damping to the exponential. If I come back here, this is the response for a phugoid, which is a sinusoidal component and an exponential component which will decay, or it may increase the envelope also depending upon the sign. And if I want to look for time to double, then I can easily write A e to the power zeta p omega p t naught plus T2p is equal to twice A e to the power zeta p omega p into T naught. And when I equate this, I find the expression T2p is ln2 by minus zeta phugoid omega phugoid. And you could see that if I want time to double to be positive, then zeta p omega p should be less than 0, and omega p is never less than 0. So the only way it could be possible is the damping ratio is negative. Then only we talk about time to double. That means it's an undamped system. Okay? So this is undamped. So we say phugoid is undamped. Second, if zeta p is greater than 0, then this time to double is no more valid. So this is now interpreted as time to half, and that is ln2 by zeta omega n phugoid or omega phugoid. So that way, level 3, you could understand if time to double is 55 seconds, that means what you are telling that the airplane has a divergent undamped phugoid, but still if it meets this criteria, pilot, by putting extra effort, excessive of course in that nature, will be able to control the airplane to safety. Okay? This is what? What is level 1? If zeta p is greater than 0.04, fantastic. Not much effort on the pilot. But let's say it is not greater than 0.04, just greater than 0. So zeta p is basically positive. So then also handling qualities will be okay enough for the pilot to put extra effort. And this is level 3 where we are talking about time to double, means the phugoid is actually undamped. But as long as this is greater than 55 seconds, the pilot will be able to control the airplane to safety. Okay, that is the understanding. So that is the level 1, level 2, level 3 handling qualities expressed in terms of zeta and omega n for the phugoid mode. Remember, that is exactly I was telling, we will be postulating every requirement through zeta p and omega n. Okay? It reminds me one thing, please understand, unstable doesn't mean uncontrollable, right? Nowadays modern aircraft are statically unstable. So unstable doesn't necessarily mean uncontrollable, right? Okay? So if the phugoid is undamped, it doesn't mean I cannot control it. But as long as this phugoid has this criteria satisfied, then controlling the airplane by putting extra effort with the pilot will be well within the handling qualities for level 3 requirement. That is the understanding. Okay? Or to tell this, suppose at some altitude the phugoid damping is just 0.02. So now you have to use the SAS to ensure that for that time the phugoid damping becomes more than 0.04. That is where the SAS is important. Right? Now this was phugoid, and now we are talking about short period. Mostly you find the SAS is used for short period, and short period requirement is, before I come to short period, please remember phugoid damping for a glide phase goes inversely with CL by CD, right? So if you want to increase the phugoid damping, best way to increase is decrease CL by CD, right? So that concept should come from there. That you have to fly such a way that at such an angle that CL by CD is not that high, or you increase the drag, okay, by putting some surface at that time. So with that concept, you can increase the phugoid damping for a gliding phase. Now let us come to the short period. When it comes to short period, the requirement is this. if I draw it like this, this is category A and C, and this is category B. This is a flight phase. You know, category, when I say it's flight phase, we are talking about. And level, if it is a level 1, then zeta short period should be minimum, and this is maximum. So minimum should be 0.35, maximum should be 1.3. Similarly, for category B flight phase, zeta short period and zeta short period, this is again zeta short period maximum, zeta short period, this is maximum and this is minimum. For this it will be 0.3 and 2.0. Please understand, for category A and category C airplane, for level 1 qualities, the short period damping ratio minimum should be 0.35 and maximum it could be 1.3. For category B flight phase, for level 1, the short period minimum should be 0.3, the damping ratio should be 0.3, maximum 2.0. Okay? For level 2, if you see, it is similarly it is 0.25 and 2.0, here it is 0.2 and 2.0. And level 3, which is very rare, level 3, we need 0.15 and this is 0.15. But this is, we put asterisk marks, it may get reduced as we are going higher and higher altitude. So, and this is the type of level 3, very, very rare. There are other criteria, other constraints come. To focus here level 1 and level 2, and the point which I was trying to draw that it is finally on the damping ratio, and soon you will find the natural frequency also will come into the play. Okay. Please understand one thing. In the dynamics, whenever we wrote the equation, the response had e to the power lambda t, then sine, all those things, depending upon it is oscillatory or it is just first order response. This e to the power lambda t, that decides the amplitude envelope and also decide whether it is going to divergent or it is going to converge, whether it is going to reduce or going to go on undamped like this, right? So that is why zeta plays an important role, right? If I talk about spiral, then it is, if I write class 1 and 4, by now you know what is class 1 and 4, and here, if I draw a line like this is flight phase category, flight phase, or which is category, cat. Then I have level 1, I have level 2, I have level 3. You fight for category 1 and 4, for flight phase, let me draw a line to that. For flight phase A, B and C, for level 1, for A it is 12 seconds, and for this is 20 seconds. What are these 10 second, 12 second and 20 second? These are time to double the amplitude. Okay, we're talking about spiral. This time to double the amplitude. That means again it is saying, when you're talking about time to double means it is showing undamped, but unstable doesn't mean uncontrollable. Okay? For level 2, it is 12 seconds, 12 here, and here it is 12 seconds. And for level 3, it is 4 seconds, it is 4 seconds. Right? And for 2 and 3 class of airplane, this is flight phase all flight phase, A, B, C. This is 20 second, 12 second, and this is 4 second. Right? And you could see when I'm giving a guideline to the designer to ensure the handling qualities as per level 1, level 2, level 3, what I'm telling to the designer, ensure that if you want a level 1 performance, then time to double should be of these values for category 1, category 2, category 4. And when I am talking about time to double, that means I am talking again in terms of zeta and omega n. Right? You have seen the expression of time to double. Okay? And this is typically, if you are allowing it to double, then I am talking about spiral divergence, undamped. Okay? And these are, of course, when I say these seconds, this is minimum time to double. These are all, you understand that, minimum time to double. Why it is minimum? Because if it is too fast, then it will be difficult to control. Right? So that is why the restriction is on minimum time to double. So after spiral, we will again come back to, I will strongly suggest you people should read or Google search and have more insight. After spiral, now we will see minimum Dutch roll frequency and damping. Let me write. Again, this is level. Again, it is flight phase, which is category. Flight phase. Then comes class. You see, we have been always talking about this thing, class. And then it is minimum zeta Dutch roll. This is minimum zeta Dutch roll, omega Dutch roll, natural frequency Dutch roll. Also minimum omega Dutch roll frequency. It is postulated, or the specifications are given like this. If it is for level 1 qualities we are looking for, and if you have, let me draw a line, if you have two types of class, 1A, 1B, this is class 1, class 4, class 2, class 3, then these values are, for 1 and 4, it is 0.19 minimum, here also 0.19, here 0.35, again 0.35, this is 1.0, and this is 0.4. This 0.4 star we have put, this may change based on the customer's requirement. These are finer details, so you please try to understand for the level 1 handling quality, they have been specified now by minimum Dutch roll damping ratio, also the product zeta d, omega d, and also minimum Dutch roll frequency in radians per second. For B, it is all 0.08, 0.15, and again 0.4 star. For C, for flight phase C, again you will see that for 1, 2, and 4, it will be 0.08, 0.15, this is 0.08, 0.15, and 1.0. And for 2 as well as 3, there are different variation of category class 2. So I am mentioning both. You will find it is again 0.08 and 0.15 and 0.4 again star. Similarly, you will find for level 2, level 3. So I don't want to really make your life miserable by going on writing all this. What I wanted to communicate to you was, when you're talking about the handling qualities, you have seen for phugoid, for spiral or for Dutch roll, these are primarily decided by the damping ratio and natural frequency or their combinations. Those who are interested to know exact numbers, I suggest them read latest airworthiness requirements. You can Google search, go for textbook. These numbers goes on changing depending upon the technology, depending upon the control system you have got. Okay, these are some guideline numbers, right? What is the important message is, we need to know how to find zeta d and omega n. We also need to know how can I change zeta d and omega n, because I know the zeta or damping ratio changes with speed, changes with altitude, right? You cannot design an aircraft by laying out this component where the zeta will not change, because zeta depends upon density, speed. So whenever you require the different values of zeta and omega or different handling qualities, the SAS is very handy, right? That is why we are designing SAS. Okay.